All right, welcome back, everybody. So we'll start right away with the question on Zoom and take it from there.
Okay, so a question from Zoom. The question is a bit long. So the student asks, did I get correctly that these documents stored are systems to store objects or elements of data files that cannot be covered into tables? Therefore, here the word document is used referencing to objects or elements.
Yes, so this is absolutely correct. This is what the word document stands for. It can be a collection of JSON objects or a collection of XML documents. Just keep in mind that a document typically in XML has a top-level element right below it, but we would still consider the document, the XML documents, to be the top level. But essentially, an XML document contains exactly one element inside. So yes, this is what the word document means. This is what we refer to, and we have in mind XML and JSON when we talk about document stores. Yes, you're also correct that document stores can store data that does not fit into tables because it's able to store data that is nested, and it's able to store data that is heterogeneous, meaning that it's also able to have collections that do not have any schema. Right? In a relational table, you need a schema. In the document store, you don't need a schema. You could even store a huge mess. You could have a collection with 1 billion JSON objects that are totally random, that have nothing to do with each other, and it's going to be done perfectly well by a document store. It turns out that you can still store relational tables in a document store because you know that a table can be seen as a collection of flat homogeneous JSON documents. So you could convert very easily a relational table to a document store. And actually, many people do the mistake of using document stores to store data that would in fact fit in tables. And that is not necessarily a good idea. It was done mostly because of the hype. You know, MongoDB is the next cool thing, so let's use MongoDB. But the thing is, you need to understand that having a system that gives you more flexibility, that makes the schema optional and that allows you to nest data and that allows for heterogeneous data, it comes at a cost. And the cost is first performance, because it's going to be a bit slower than PostgreSQL, for example. If the data is structured, it's going to be a bit slower, and it's going to be lower level. Because in a relational database management system like PostgreSQL, not only is it fast, but you also have the benefit of the SQL language. Right? Very high level, you write your SQL and so on. So it's very convenient, and it's very high performance. So if you use a document store, you really need to make sure that you use it for good reasons. And that you use it, for example, because you want the schema to be optional because your data is not completely clean, or you need the nestedness, right, that you cannot typically have in a relational database management system. I will add one more thing, is that classically, the relational database management systems do not have nestedness. Classically, in the early versions, because you have the first normal form, so atomic integrity. But because of the whole hype with XML and JSON and document stores and so on, the vendors of relational database systems starting adding types for objects and arrays. And so now if you go to PostgreSQL, you will find types for objects and arrays. So in PostgreSQL, now you can have nested data also that is supported. There are now extensions of SQL that do that, right? And so it made its way a little bit back into the relational database management systems. But then you will hit the issues that I told you about with trying to hit the data with a hammer, right? That it's not enough, basically, to handle all of the cases. So what I'm saying here is that the frontier has been blurred a little bit because of some of these things that flew back into the relational database management systems with JSON object and JSON array types in PostgreSQL, for example. Does it make sense?
Yeah, let's wait for the response. So there's no response. Yes, so I assume it's okay. The student say yes, it makes sense.
Okay, awesome, perfect. All right, and don't hesitate to interrupt again That's the benefit you get from not binge watching on YouTube. It's live, so you get to interrupt me and ask questions, right? The people who watch later on YouTube, they cannot do that. They can still send me an email, but not interrupt. All right, so now that we have that, I told you there is a cost of the flexibility of not having to have a schema, and the cost is that what I'm going to show you is lower level than SQL. Right? And we'll come back to a query language that is as good as SQL a bit later. But you will see that what I'm going to show you here is not the level of SQL. The first thing that you notice when you use MongoDB is that if you want to access it, you need to access it in some programming language. It's not a language of its own, right? SQL is a language of its own. If you connect to PostgreSQL, you just type SQL and that's it, right? But in MongoDB, you need a programming language. That programming language can be JavaScript, can be Python, can be many others, right? But JavaScript and Python are probably the most popular. JavaScript was the first one that was the first ones that was very popular with MongoDB. And now I think more and more people use Python with MongoDB. And so this, in fact, what you see on the screen is actually JavaScript. More exactly, it's a JavaScript API, a JavaScript library. API, for those of you who don't know what it means, it's Application Programming Interface. So an API is just a library exposed in Python or any language that allows you to call certain functions in a certain way. That is an API. Pandas is an API, or Python library. So we have an API in JavaScript, and we also have an API in Python that allows you to access the database. So that tells us already that's low level, because we have to do it from some programming language. So I'm going to show you a few queries. So this is the query that just outputs the whole collection. How do you do this? Well, you need to do in JavaScript db dot, so db is always db, and then the name of the collection, dot scientists, that's the name of the collection you want to access, dot find, and then that gives you, that returns the collection. So you can do it on a shell. For example, if you connect to a MongoDB shell and type that, it will show you on the shell the first objects. If there's a million of them, it's not going to show them all. Maybe it's just going to show the first ones. But if you're actually writing a computer program, you can also write a loop that iterates over all of the objects that is returned, right? All right. So the find function does that. You can either call it without any parameters, open, close parentheses, or you can call it with an empty JSON object. The two are totally fine. Right? So all of that returns the entire collection. I'm assuming we already imported data in there, and it displays this. I have this rectangle here that I put everywhere. That would be the SQL equivalent, if it exists. The SQL equivalent of that would be select star from scientists, right? Just returns the content of the collection. Everybody with me? That is the simplest possible, right? That's just outputting the contents of the collection. So now, what about selection? You remember that selection means you filter the records and keep them with a certain predicate. That corresponds to the where clause in SQL. And the way we do it in MongoDB, in this API, in this JavaScript API, is that we pass a JSON object inside the find function. So that would be the one that is empty right here. So it's empty, so there's no filter, but you can add a filter. In that case, you say, okay, I want theory to be equal to relativity. That would be in SQL where theory equals relativity, right? But in the API of JavaScript, you pass that as a JSON object, right? It's kind of a pattern that you're looking for in JSON. And that is going to return all of the JSON objects, the JSON documents, that match your filter, this one and this one, right? That are going to be returned. And now you start seeing the fact that it's an API, right? Because now it's not just a high-level query language. You actually have to build a JSON object that contains your filter. And you will see that can actually also become complex in the way that you design the JSON object. Now, how do we project The projection, that's when you take specific columns, right, of your table. So what if we project to first and last? Well, we do that by chaining a project function call. So it's dot find blah, 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 dot project blah, blah, blah. And in project, you say, okay, first and last. First one, last one. And that returns what you see at the bottom of the screen. That would be equivalent to select first, last from scientists where theory equals relativity. Now, what I want you to look at to really understand that it's an API and not a query language, and to see where that is a bit itchy for the end user, two things. First, here, there's no parentheses or anything. You just write select first, last, so it's very natural to write. Here, you have to realize that you have dots, you have to open a parenthesis, open an object, close the parentheses, open a parenthesis, another function called chains, open an object, close a parenthesis. So the way you see the limits of an API in usability is that you have a lot of opening and closing parentheses. And you can lose a lot of time opening them well and closing them well when it becomes more complex and so on, as opposed to a query language where you don't have to worry with that. So this idea of having plenty of parentheses and function calls and so on, that is what you have in an API. And that can become cumbersome when the use cases become more complex. So that is the first thing that you can observe. The second thing you can observe is that some of the design of an API like that can be either non-intuitive or, let's say, arbitrary. For example, the fact that you need to put a 1 in here and a 1 in here is a design choice. Whoever designed the API decided that you put a 1 in here to project, and that's it. And that you either need to look at the documentation or learn it by heart. And that puts an extra burden on the user to actually have to learn this API. And this API is arbitrary because if you use another technology, another document store, they might have completely different conventions. Right? So that's not standardized as a query language would be standardized. So I just wanted to point to these two limits in terms of productivity. And I emphasize, this is not a query language. This is an API in JavaScript. This is a query language. This is an API, a library. Okay, so that's to unscare you if you find this complex. I want you to find it complex because again, that's an API, and we'll see next week and the week after that we can actually replace that all with also a query language that doesn't have these issues. When you use 0 instead of 1 here, that's also a design choice. It means you project away. So that means you remove the theory key, right? You exclude the theory key. That you don't have in SQL, right? That's something you do in a document store. In SQL, you could just enumerate all the columns you want and not put those you don't want. But the reason why it makes sense in the document store is that if you have data without any schema, you might not know all of the keys that there are. So it might be convenient to just say, okay, everything except this and this and this, right? Then you put them with a 0. Everybody with me? Right? All right. Then what happens if we want an AND, a conjunction, where something and something else and something else and something else? Well, you just accumulate them in your JSON object. If you put plenty of more keys in that object that you pass to finds, that will be understood as an AND. So here it's theory, relativity, and last Einstein. All right? That is also a design decision. It could have been or, right? It basically just whoever designs the API makes this decision. The only way you know that is looking at the documentation, right? Just because it's documented in this way. So this is AND. The OR is done in a different way. If you want an OR, then you see some other conventions that are design decisions. The first thing you see is that it has this dollar sign in the key. And the dollar in MongoDB is a special character. It's considered special. So when you have a key in a query that starts with a dollar, it means special meaning. So $OR is followed by an array, and then you have two objects that would be the filters, And then it has the semantic of either the one or the other. So last is Newton or last is Einstein. And again, here you see it's an API, it's not a query language. Because if you compare the two, you have these two things I told you earlier, a lot of opening and closing parentheses, opening and closing curly brace, opening and closing array, and so on, becomes very complex to write. It feels very like programming. In SQL, it's much simpler, right? In a query language, you don't need to bother with all these opening and closing brackets and parentheses. The second thing is again, I insist, the design of the API. That could have been different, right? The only way to know is to look at the documentation. Dollar could have been something else than dollar, right? Could have been a different way. Why an array? That's also because it's documented as such, right? And again, you need to look at the documentation to know that. So it requires a bit more work. And if you move to another technology, again, that might be a completely different design in there. But it works, right? It gives you an API that allows you to work on this messy data. If you want comparisons, that's the $GTE that takes care of it. So you see also it would be easier in SQL. Publications is greater than or equal to 100. Would return the first and the third documents. Okay. Now, coming back to this query that I've already showed you before, I would like to show how it plays with heterogeneity. Because the examples that I've showed you before, these were actually tables, the way that the data was structured. But here you have some different kind of data where there is a missing field. In the fifth object, theory is not even present, right? Well, in that case, that query would just not return it, right? So when you say theory relativity, it finds all the objects that have a key called theory at the top level, and the value is relativity. So the fifth object would just be excluded, right? Everybody with me? Right? So it supports, it's not going to throw an error, it works. If you want to specifically take the one that doesn't have theory, you can put a null in there, theory null, in your query. That is also a design choice. They made the design decision that null is the same thing as absent. That's a design decision. So if you say theory null, it's both going to return the objects where theory is null and those objects where theory is absent. Technically, in the JSON data model, it's different. If you have an absent value or if you have a value associated with null, these are different things. But here they assume it's the same. And so theory null is going to return the documents that don't contain any key theory. All right. And again, that design decision differs from system to system. There are other systems that will distinguish between null or absent, and there are systems that consider it to be the same. The only way to know is to look at the documentation, figure it out. So far, so good? Right? Okay. Now, what about nestedness and querying inside? What if you want to go inside an object called name and then in that object find the key that's called first? Then again, you need to use a dot. And here again, you see it's a design choice. They made the decision that the dot is a special character, just like the dollar. The dot is a special character. So this query is not going to look for objects that have a key that is exactly named dot first. No, it's going to look for objects that have a key name in which there is another object in which there is a key first. Right? So again, that's a design choice by the team. And again, you have to look at the documentation to know that. Okay? So that would return the first two and not the next one. A common mistake people do is this. They would try to write the pattern of name containing first Albert. But in fact, and that's also a design choice, if you do that, it's looking for an exact match. That is going to look for the key names where the object is exactly first Albert and nothing else. So it will only return document 2, but not document 1. And again, I insist, again, that's an arbitrary decision. It's a design choice. Another system might do it differently, right? So this is just part of the API, the way that it's working, right? Another decision that's part of the design is when you write here theory special relativity, it's not only going to return the documents where theories is equal to that, it's also going to return the documents where theories is an array and one of these values is this one. So it's also going to return this, right? That is also a design choice that you know by reading the documentation. And so by now, I hope you realize that the learning curve of an API is a bit steeper than the learning curve of a query language. Because in a query language, things are designed for ease of learning and ease of use. In an API, you just have a lot of conventions that you cannot guess. You really have to read the documentation and so on. And then you have to keep track of it. You might not even know everything that there is to know because that's a very large documentation. So what I want you to focus on is really the limits of that. The fact that when you have an API like that, it's tougher to learn for this reason and tougher to write. But that gives you an example of API. Another operator with dollar is $in, where you say that can be one of these two values. University has to be either ETH Zurich or EPFL, right? That is another example of operator. Do you agree it's equivalent to an OR? That would be equivalent to $or University ETH Zurich, University EPFL, right? It would be the same thing. Okay? So that is another example. So now I showed you find, I showed you project. There's others, there's also count. For example, if you append a count here, that is going to return to you an integer that is the total number of results of the query, right? So dot count. You have also dot sort. Dot sort is going to sort the results of the query. And here again, design choice, design choice, design choice. Don't be scared. -1 means decreasing, +1 means increasing, right? That is the design choice that was made for the sorting, okay? And also, and again, don't be scared or don't scream. If you look at the Python API, it's going to be different from the JSONing API. So the objects you will see in the Python API will not be the same objects as you will see in the JavaScript API. That's also a source of confusion because when you Google the documentation of MongoDB and you look for the syntax to do a certain things, you might actually be doing it in Python and you Google it, but you will be on the JavaScript API. And of course, you have to check that you're looking at the right API, that of the language you're actually using. That is a common source of confusion with the APIs. And again, that has to do with the fact that it's APIs. And so the API might be different between JavaScript and Python. You also have skip and limit that corresponds to limit and offset in SQL, right? But here again, look at all these parentheses and curly braces and so on, compared to SQL, where you would just write order by founded desk, limit 10, offset 30, right? So I want you to see that the API takes a bit more work to write with all the parentheses and chain function calls than a query language. Okay, there's another function called distinct. That would be an equivalent in SQL of select distinct, blah, blah, blah. So that is going to output all the distinct values for a specific top level key. Right? And then you have what's called aggregation pipelines that look like this. Again, these $, $, everywhere, all these parentheses and curly braces and so on. This here is called an aggregation pipeline. But I'm not going to go into any details of that. Why? Because you've already seen that. Not that specific syntax, but you've actually already seen that. Does this remind you of something? The pattern of that? Who sees that it's basically Spark? It's basically a chain of transformations. Right? So this is why I'm not going into the details of that. That's basically Spark. Similar, it's not exactly Spark, but it's similar to Spark. So that would be a filtering, followed by a grouping transformation, followed by a sorting transformation, followed by limit 5 would be probably a take 5 as an action in Spark. So that's it. It's just similar to Spark. So since you already know how to use Spark, if any one of you wants to go ahead and use MongoDB aggregation pipelines, it will be very easy to learn. You need to look at the documentation, of course, the way it's done and so on, that you cannot guess, right? You have to look at the documentation. But what I can tell you is that this is going to be easy to learn because of the knowledge you already have of Spark, right? So you can generalize in this way. Okay, and so this is why I'm not going further than that. This is basically just to show you. I told you it's not a data lake. It's an ETL system like PostgreSQL. And that means that in order to be able to query the collections, you first need to create and populate the collections. How do we do that? In SQL, you know that you can use create table and insert into insert values into and so on. In MongoDB, you have functions like insert, update, and delete that you can call, and that's going to modify the data in the collection. You have every time one or many, right? Insert one, insert many, update one, update many, delete one, delete many, right? You have the two versions. So that is inserting a new object in the collection. That is updating an object. So it's looking for the objects that have last equal to Einstein, and then it's going to set century to 20. Again, you cannot guess that syntax. That is a design choice of the API. The only way you can know that is look at the documentation. Right? So this is the API. And it might even be different in Python than in JavaScript. And delete is going to just remove from the collection the documents that match this. Delete many, so it's going to delete them all, right? Okay, so just to show you, that's something we do not have in Spark, right? In Spark, I did not show you any way to update anything. In Spark, you drop it on HDFS, you drop it on S3 as a file upload, and then you query. Here, you cannot do that. You really have to explicitly insert, update, delete. MongoDB and many document stores also have some command line utilities. So if you have a JSON line files that you maybe got from HDFS or S3, there is a script that allows you to import the JSON lines file into MongoDB, right? But you need to be patient, right? If it's a very large file, it takes time for it to import it into the system. So far, so good, right? Okay. Now, one more thing is because we modify the collection, we need to know about the granularity. Meaning, what if many people modify the collection at the same time? Well, the granularity is the documents. That means that there cannot be two people modifying the same document at the same time. It means that if two people want to modify a document, they need to queue. It's going to be first one person and then the other person that modifies it. It has to be queued. But for the collection, that's no problem at all. You can have 10 people modifying the same collection at the same time. That's no problem, right? It's just the documents that cannot be modified at the same time. So that's what we call the granularity of atomicity. Atomicity here has nothing to do with atomic values in objects. That's atomicity in the sense of transaction, that the fact that it's first one person and then another person, right? Okay. Now, I've insisted a lot on the fact that what I've showed you is an API, it's the JavaScript API of MongoDB. Are there query languages? The answer is yes. I'm going to show one to you next week. That's called JSONic. That's I was involved in that one. That was 15 years ago. It turns out that by now there's 30 of them. I'm trying to keep a list every couple of months. There's new people who invent a new language and so on. It has not consolidated like SQL has. For tables, people don't even argue about that. It's SQL. Nobody in their right mind would consider using something else than SQL for a table, another language. They could still use an API like Pandas, but the language would be SQL. For trees, we need to be patient. People have not agreed yet. I hope it will happen one day, that there will be at some point a convergence towards a unique standard. Technically, Xquery is already a standard. By the W3C, there were people from IBM, from Microsoft, from Oracle, and so on involved in the standard. For some reasons, not everybody has adopted it. JSONiq was an attempt to make it more appealing to the JSON community. But yeah, it needs a lot of patience. GraphQL, I think, is Meta's attempt to come up with a language, but GraphQL is a lower level language. It's not a query language at the same level as SQL or Xquery or JSONiq. Uncle is another one. There's 30 of them, basically. The tough part of query languages, and the reason why it's also having some difficulty catching on, is that when you design a language, you need to do it the whole way. When you design a language, it means you need a whole specification for every corner case of every single expression of the language, all the error codes, and so on. This takes a lot of work. Designing a language, imagine you throw people on a language, you're a company, you want to design your own language. We're talking about millions of dollars in here, if not tens of millions of dollars. Because it's one thing to document a language as a prototype. You just spend 1 hour on it, you give a few examples and so on, you implement a simple prototype. That is the easy part. But designing every single corner case and every detail of the language, that takes years and many people to do that. So Xquery, for example, was 20 people over probably now 20 years, right? And you can do the math of all the money and the resources that this actually costs. Yep, so this is what I wanted to say about this, and hopefully it converges. All right, but when it converges, you will be ready because the way it will converge will be similar to what I will show you next week. All right, so I told you how MongoDB works. Very large collection of small objects, not more than 16 megabytes per object. I showed you the API, the JavaScript API. There's also a Python API, so just so you know. And now I'm going a bit in the architecture, not so much, just a little bit. But I'm not going to surprise you that much because these are things we've already seen. First, I think it's not going to be a surprise if I tell you that when we store the documents, we replicate them. We store the documents multiple times. Shouldn't surprise you, right? It's the same in HDFS. We also replicate the blocks. So it's a very common thing to do. And we also do that here. So it means that a collection is going to be stored redundantly. That's the first thing. That is not really new. The second thing is that we are going to partition the collection. That also shouldn't surprise you. We've seen it plenty of times before. We've partitioned files in HDFS as blocks. We've partitioned in HBase as regions and even stores. So that shouldn't surprise you either, right? That we would partition the collections as well. So we both partition and replicate. That's pretty standard. The partitioning in MongoDB is typically done based on an indexing key. You basically decide, for example, the social security number, if you have a collection of people, AHFAO, and then you sort it and you design your partitions as intervals. For example, if it's the last name of the people, then A to E is the first partition, F to P the second one, Q to Z the third one. Right? That's how MongoDB does it. So it's more explicit than in Spark, right? When Spark partitions, it just does its own thing in the background and you don't really know how. MongoDB does it more explicitly. In MongoDB, you actually know how it's partitioning. All right. Then we have a name for a partition, or more exactly the computers that store a partition. It's called the replica set, and it looks like this. Now, this should surprise you, because that's actually not the usual architecture. The usual architecture we had in HDFS, in Spark, in HBase, everywhere, was a centralized architecture where we had a single coordinator node and then all of the worker nodes below it. But here it's different, because now we have somehow that architecture for every partition. So here I have 3 partitions, and I have three sets of computers here. So that is specific to MongoDB, the fact that it's done in this way. Yes?
Yes, a question from Zoom. It might be related to the previous slide. So the student asks, how are the documents physically stored in document stores?
Mm-hmm. So I can first answer how it's not stored in document stores. It's not stored as JSON files. That would be my first answer. So it's not like data lakes the way you would do it in MapReduce or Spark. Instead, it is stored on disk in a, I was almost saying proprietary fashion, hidden from the user. In fact, it's stored as zeros and ones. For MongoDB, they call it BSON. BSON is their own approach to the way they store the documents on the disk.
Yeah.
Yes?
So the student comments that the question was before this chapter. So yeah.
The question was, yes, that was at 9:45. Yes. So now you have the answer to the question, right? Okay. But still, I might not have said it explicitly before, the fact that it was stored as BSON, right? So BSON is just a proprietary format that is specific to MongoDB in the way it's going to store the JSON documents on disk. You can see it as a form of compressed JSON. It's a compressed form of JSON, but not as compressed as Parquet, right? Because Parquet would imply that there is a schema, but here there is no schema, so generally. So that would be just a compressed version of JSON, but you as the user should never see it. The only way you interact with MongoDB is with the JavaScript and Python APIs. So you never see these details, but it is stored on disk, on the local disks of these machines in the BSON format, hidden from the user. Does it answer your question?
Yeah, he says thank you.
Yeah, all right, perfect. Okay. So then we have these replica sets or shards, shards, partition, chunk, split, block. There are so many words depending on the technology, but it's all the same. Now, why do we have these multiple machines? So first for replication, because we want to replicate the data. So it's going to be stored, in that case, 3 times every time. I'm not sure I think this is running out of battery because it's no longer, oh, that's because I'm on Zoom. That's why it's not clicking through. There you go. Now I want to show you something else. We are going to replicate multiple times. So whenever you insert something into the document store, we are not using HDFS, right? So when you insert something, we cannot rely on HDFS to do anything. So it's MongoDB that's taking care of it. And what happens is that you connect to the top machine of the replica sets that you want. So you need to figure out which one of these 3 is responsible for the document you want to insert. Once you have figured it out, you, and more exactly, the computer program that you're using, is going to connect to the appropriate replica set, is going to send the documents to the machine at the top level here and request that it adds the document in the collection. That machine is going to acknowledge and say, yes, I've added it on my own machine. So now it's written to the disk of that machine. And it's also being forwarded to the other computer so that they can also store a copy for redundancy. And then you start getting acknowledgement. So this one acknowledged, and maybe you decided that 3 is good enough. And so that means that you wait until you get 3 confirmations, and then you return to the user. You confirm to the user, now that's fine. It's already been stored 3 times, you're safe. And then you can still continue to replicate in the background. You might store it a fourth time and a fifth time, but you've already confirmed to the user that the minimum of 3 has been reached, right? All right, so that's how it works, right? You replicate on the machines and wait until the minimum is reached. So a bit similar to HDFS, but it's not HDFS. Here, it's really MongoDB that directly is running on all of these machines and that stores it on the local disks. Yes? How is it connected to this? So this here is one of them, right? So you have this for every one of these. So the idea, the way that it works is that when you want to insert a new document, you explicitly know which partition it corresponds to. So imagine you want to insert a document starts with the letter D, right? The key based on which it's partitions. So if the key of the document you want to insert, the value starts with D, you know it's the first one. So what's going to happen is that you will connect to shard 1, to the primary machine of shard 1, and then it propagates to the secondaries of shard 1. When I say you, I mean more exactly the MongoDB software that is running on your machine, right? When on the shell, you call this insert documents, the MongoDB software will figure out which one of these 3 it has to contact, and then will connect to it in this way. That's how it relates. Does it answer your question? Yeah, awesome. I'm trying to think if it might be historical. You could have, right? You could absolutely imagine using HDFS to store the data. The MongoDB, I think, probably was done after HDFS was invented, but maybe HDFS wasn't quite popular yet. Let me answer your question differently, and maybe you will tell me if that helps. HDFS does not have the ability to update the data in place, right? You remember that in HDFS, you can write new files or you can append to files, but you cannot modify the data in place, right? In MongoDB, you can. You can absolutely say, I want to update this document and change that value and so on. So it means it's not a good fit for HDFS in this sense, that you cannot just so easily update a value in place. Now, we've seen that we still can build something that kind of does that, right, with HBase. HBase is able to update in place. And we saw how complex it is, right? The way it's done is that you do it in the memory, and then you wait until you have enough updates in memory, and then you flush it. So what I mean is that it's complex because HDFS is not done for small updates like this. In MongoDB, since you're writing to the local disks of the machines, you have no problem doing it in place on the local disks, right? So this is why it's a different design. Now, there are more recent developments by Databricks, so the same company that is behind Spark, something called the Delta Lake that is kind of doing that on top of HDFS, right? So it's the ability to update the JSON documents stored on HDFS. And the way they do that is very close to Git, you know, the versioning system. That when you write to Git and you do modifications, it's not actually modifying, it's just adding a new version and giving you the delta with the new version. And the Delta Lake does exactly that. So it allows you to update JSON, but instead of actually updating it, it's just creating a new version. And so it's just going to create new files on HDFS to keep recording the changes that you have in a way that's similar to Git. But it's more recent, it's more complex, more involved than this. So I would say maybe one way to answer your question is that it's simpler to just have this architecture locally on machines than to use HDFS, at least for a first prototype. Maybe I can also give you a second answer. Is that typically at least in the early days of MongoDB, the number of machines that we are looking at for MongoDB is not in the thousands. We are not looking at 1,000 machines here. In the case of HDFS or Spark, we are looking at 1,000 machines. That you can have 1,000 or 10,000 machines. In the case of MongoDB, the typical setups, you can count the machines on your hands. It's going to be like, this is a typical setup. You have 9 machines. There are people who use MongoDB with 9 machines or with these machines. And so the fact that you're not looking at petabytes of data or exabytes of data, but more like very commonly gigabytes of data, tens of gigabytes, hundreds of gigabytes, that simplifies the architecture. And it allows you to design things a bit simpler than all the complexity of the Delta Lake and HBase, right? So that was a bit of a puzzle answer in the sense that I give plenty of elements of answer, but does it help? Does it address what yes? Yeah, awesome. Okay. It's actually 10. So I have to let you go. Is there anything else? Yes, the next part was the indices, so I'll just do that next week. The indices will just be one of the nice perks of using an ETL system that is not a data lake, because that is something you cannot do on data lake. Indices are a way to answer your queries in just a few milliseconds. That is something with Spark you cannot do. Right? So I'll explain that next week, and we'll see it's similar to PostgreSQL and the way that indices work on relational systems. So why is the camera not working? I'm not sure what's happening with the system. But anyway, thank you very much, everybody, for joining us. Enjoy the exercises. If you have any questions, then send us emails or write on the forum. Don't forget to read the textbook. Spent a lot of time writing it so that you can also learn at your own pace offline. Thank you, Zoomin, for helping out with the moderation of the lecture and interrupting me for all the questions. Very glad you asked these questions. Oh, well, the video is back. So that's it. Have a good day and see you next week at 8 a.m.